Hi there, so welcome back to the channel and welcome to Excel Island, where the goal and objective is to learn and master Python over the next 100 days. Today is day 75 or 75th. We are going to continue on the course. We are continuing on the course called Sampling in Python, and we are on the last chapter, which is called Bootstrapping Distribution. Bootstrap distributions. So the last three chapters we covered introduction to sampling. We cover the different sampling methods. We also look at sampling distribution, and this is the last chapter in this course. So after this last chapter in this sampling in Python, we have one more course to complete the whole career track in this data analyst in Python career track on the DataCamp platform. That should be hypothesis testing in Python. So without further ado, let's complete this last chapter, which is bootstrap distributions. So you are going to get grips with resampling to perform bootstrapping and estimate variation in an unknown population. You will learn the difference between sampling distributions and bootstrap distribution using resampling. So whatever that means, let's get started with it. Let me just start sharing my screen real quick so we can continue. Let's continue. I also have my, let me create a new notebook for chapter. Let me just grab this. I'll still need to open this one too also. So I'm going to name it Introduction to Sampling Chapter 4. And as usual, we're going to copy these all libraries that we're going to use here also. Just run that. Then finally, I'm going to copy this line of code just to read the data set really quick here. Okay, so this is our chapter 4 and final chapter in this course.
So far, we've mostly focused on the idea of sampling without replacement. Sampling without replacement is like dealing a pack of cards. When we deal the ace of spades to one player, we can't then deal the ace of spades to another player. Sampling with replacement is like rolling dice. If we roll a 6, we can still get a 6 on the next roll. Sampling with replacement is sometimes called resampling. We'll use these terms interchangeably. If we take a simple random sample without replacement, each row of the dataset, or each type of coffee, can only appear once in the sample. If we sample with replacement, it means that each row of the dataset, or each coffee, can be sampled multiple times. So far, we've been treating the coffee ratings dataset as the population of all coffees. Of course, it doesn't include every coffee in the world, so we could treat the coffee dataset as just being a big sample of coffees. To imagine what the whole population is like, we need to approximate the other coffees that aren't in the dataset. Each of the coffees in the sample dataset will have properties that are representative of the coffees that we don't have. Resampling lets us use the existing coffees to approximate those other theoretical coffees. To keep it simple, let's focus on 3 columns of the coffee dataset. To make it easier to see which rows ended up in the sample, we'll add a row index column called index using the reset index method. To sample with replacement, we call sample as usual, but set the replace argument to true. Setting frac to 1 produces a sample of the same size as the original dataset. Counting the values of the index column shows how many times each coffee ended up in the resampled dataset. Some coffees were sampled 4 or 5 times. That means that some coffees didn't end up in the resample. By taking the number of distinct index values in the resampled dataset, using len on drop duplicates, we see that 868 different coffees were included. By comparing this number with the total number of coffees, we can see that 470 coffees weren't included in the resample. We're going to use resampling for a technique called bootstrapping. In some sense, bootstrapping is the opposite of sampling from a population. With sampling, we treat the dataset as the population and move to a smaller sample. With bootstrapping, we treat the dataset as a sample and use it to build up a theoretical population. A use case of bootstrapping is to try to understand the variability due to sampling. This is important in cases where we aren't able to sample the population multiple times to create a sampling distribution. The sampling process has 3 steps. First, randomly sample with replacement to get a resample the same size as the original dataset. Then, calculate a statistic, such as a mean of one of the columns. Note that the mean isn't always the choice here, and bootstrapping allows for complex statistics to be computed too. Then, replicate this many times to get lots of these bootstrap statistics. Earlier in the course we did something similar. We took a simple random sample, then calculated a summary statistic, then repeated those 2 steps to form a sampling distribution. This time, when we've used resampling instead of sampling, we get a bootstrap distribution. The resampling step uses the code we just saw, calling sample with frac set to 1 and replace set to true. Calculating a bootstrap statistic can be done with mean from NumPy. In this case, we're calculating the mean flavor score. To repeat steps 1 and 2 1,000 times, we can wrap the code in a for loop and append the statistics to a list. Here's a histogram of the bootstrap distribution of the sample mean. Notice that it is close to following a normal distribution. Best get bootstrapping.
Okay, let's see bootstrapping in action. It's kind of funny though. It says bootstrapping is, in some sense, the opposite of sampling from a population. Sampling treats your data set as the population and you generate a random subset. Bootstrapping treats your data set as a sample and uses it to build up a theoretical population. Okay, drag the item to the correct bucket. Bootstrap samples should be the same size as the original sample. That's true. Okay. Mm, that should be true though. Let's give it a shot. Oh, see, this is false. So it said a bootstrap distribution consists of many replicates of the statistics of interest. It said bootstrap sample should be the same size as the original sample. That's true. Each row in the data set should have an equally likely chance of being drawn in a sample. Yes, so you have to do bootstrap without replacements. Okay, let's go. Boolean bootstrapping. The bootstrapping workflow is to generate a sample of the same size as the population, calculate the sum in statistics, then repeat the same process. So it has 2 processes. Calculate statistics of interest. It doesn't have to be the mean. You always have a statistics of interest in mind. Let's continue to another one. With or without replacements. Okay. Okay. Read the different scenarios and determine whether sampling without replacement from a population or sampling with replacement from a sample is the most appropriate strategy. Okay. Let's see. Ooh, we missed it to each other. Radical replacement reasoning. The key to deciding whether it's to sample with or without replacements is whether or not your data set is best thought of as being the whole population or not. So if you want to know whether to sample with replacement or without replacement, you have to ensure that the data set or is being the data set that you actually have is giving you information about the whole population in the area location about what you're trying to do. Okay. Okay. Let's go. Let's go. Okay, we need okay, generating a bootstrap distribution. The process for generating a bootstrap distribution is similar to the process for generating a sampling distribution. Only the first step is different. Okay. I'll be using the Spotify data sets. Okay, let's go. Let's do that here. Until we use the Spotify data set here. Okay, we use it here. Okay, it says generate a single bootstrap sample from Spotify sample. Okay, okay, let's generate a Spotify sample from these data sets. Now we go to Spotify. Yeah, just Spotify. So I want to select only certain rows and column. These three columns are actually selected in this Spotify sample. We have the artist name column. Let's check. This is the artist here. The song name, the name, and this danceability column. including the index too. If I can't use Spotify sample, oh, oh, hold on a minute. Let's see. So let's generate a single bootstrap sample from Spotify sample. Let's see. Oh, oh, let's get rid of the index column. Have our Spotify sample here. This is the artist name and the ability, just like we have here. Okay, let's see if this is correct. Oh, so you didn't specify the frag. Okay. What's included index? So the index is already included already. Okay. Let's continue with this. Okay, the facts also be equal to 1. That should be solved for the spice sample. Let's submit and see. Okay, voila, that's all we needed to do. On the next one, bootstrap sample. Let's do the same thing here. So our one is called Spotify sample. We just call it one also, just to make things easier. Oh, I see we generated this sample. Okay. Yes, generate a single bootstrap sample with Spotify sample. Okay, we've done that. It says calculate the mean of the danceability column by using NumPy. The mean danceability column. I generate the danceability column mean. Let's see that. Let's focus on the column that we want. It's the unstability column. What I mean here. Okay, let's do the same thing here also. This mention is 0.59. 0.59 is quite similar. And finally, we replicate this expression provided 100 times. Let's replicate it around 1,000. Okay, 1,000 times. So that will be for range. That's a for loop. 1,000 times. That's all we need. And voila. And see the results. Let's see it in action here also. Ooh, still a lot of numbers here. When I create a bootstrap distribution by drawing an histogram of the mean of the unstability 1,000 times. Let's do the histogram. To see what we've done. Let's take a look at it here first and see. And voila, look at the histogram. Interesting. Yes, we have similar results here. Let's submit that. And boom, we nailed it. Beautiful bootstrapping. From the smaller samples of specified songs, we can estimate the mean danceability statistics in the population. Since we have a distribution of statistics, we can even quantify how accurate our estimate is. Okay, so let's continue.
In the last video, we took a focused subset of the coffee dataset. Here's a 500 row sample from it. Here, we generate a bootstrap distribution of the mean coffee flavor scores from that sample. .sample generates a resample, mp.mean calculates the statistic, and the for loop with .append repeats these steps to produce a distribution of bootstrap statistics. Here's the histogram of the bootstrap distribution, which is close to a normal distribution. Here's the mean flavor score from the original sample. In the bootstrap distribution, each value is an estimate of the mean flavor score. Recall that each of these values corresponds to one potential sample mean from the theoretical population. If we take the mean of those means, we get our best guess of the population mean. The two values are really close. However, there's a problem. The true population mean is actually a little different. The behavior that you just saw is typical. The bootstrap distribution mean is usually almost identical to the original sample mean. However, that is not often a good thing. If the original sample wasn't closely representative of the population, then the bootstrap distribution mean won't be a good estimate of the population mean. Bootstrapping cannot correct any potential biases due to differences between the sample and the population. While we do have that limitation in estimating the population mean, one great thing about distributions is that we can also quantify variation. The standard deviation of the sample flavors is around 0.354. Recall that pandas.std calculates a sample standard deviation by default. If we calculate the standard deviation of the bootstrap distribution, specifying a DDOF of 1, then we get a completely different number. So what's going on here? Remember that one goal of bootstrapping is to quantify what variability we might expect in our sample statistic as we go from one sample to another. Recall that this quantity is called the standard error, as measured by the standard deviation of the sampling distribution of that statistic. The standard deviation of the bootstrap means can be used as a way to estimate this measure of uncertainty. If we multiply that standard error by the square root of the sample size, we get an estimate of the standard deviation in the original population. Our estimate of the standard deviation is around 0.353. The true standard deviation is around 0.341, so our estimate is pretty close. In fact, it is closer than just using the sample standard deviation alone. To recap, the estimated standard error is the standard deviation of the bootstrap distribution values for our statistic of interest. This estimated standard error times the square root of the sample size gives a really good estimate of the standard deviation of the population. That is, although bootstrapping was poor at estimating the population mean, it is generally great for estimating the population standard deviation. Let's play with some standard errors.
Okay, so let's see this in action. So bootstrap statistics and population statistics. Bootstrap distribution statistics can be used to estimate population parameters, but you can always rely on them to give an accurate estimate of unknown population parameter. Should the mean and the bootstrap deviation of the bootstrap distribution would be used to estimate the corresponding values of the population? Should the mean mm, that's it. So the mean of the bootstrap distribution will always be near the sample mean, which may not necessarily be very close to the population mean. So super standard error reasoning. If the sample is not closely representative of the population, then the mean of the bootstrap distribution will not be representative of the population mean. This is less of a problem for standard errors. There's a lot of technicality to know there. So let's continue from here. So we have sampling distribution versus bootstrap distribution. Let's see. So we want to do for 2000. Oh, I didn't include the keyword in. Oh, Checking it. It's saying that there is with the typical there's problem with the structure of your code. So mean popularity 2000. Where's my error coming from? Why is going from this mean popularity? Okay. Let's see. Oh, I'm having an error in my code. Let's see. I'm having a little bit of error there. Let's figure it out. Okay. Let's see where the error is coming from. Oh, oh. I'm having an error though. Impopularity. Okay. Oh, that's the error we're having. Okay. We're actually repeating too many line of code there. Let's see. Oh, that'll be Spotify. Actually, sampling distribution results for 200 samples. That's a lot. So let's do dot edge. Sample 500 rows of the sample replacements. Right, I did the bootstrap distribution. What do you need for a bootstrap distribution now? Oh, okay, let's see it in action. Oh, oh, I can't use dot edge there. My bad. Oh, well, we have a result there. There's a lot of samples too also. Let's continue though. Learning distribution. The sampling distribution and the bootstrap distribution are closely related, and so is the code to generate them. So they are quite related, and the code are also related also. Which am I getting here? Popularity. Oh, this column. Okay. What is the code here? It is absolutely here though. These small letters. Uh-oh. The middle is of it here now. Why are we not getting errors there? I'm just going to accept this one more time. It's obsessing. Why am I getting an error here? Let's forge ahead. To complete the mean popularity in 4 ways. Oh, there are even 4 ways to complete the mean popularity. Oh boy, I'm exhausted. How the pop me, how the sample me, like some distribution mean, how the bootstrapping mean. Okay, sorry, welcome back. Just a quick break there. Let's calculate the mean for all this. Okay, so we have our results here. So let's give same thing a short here also. Mine is just 45. Oh, why is not seeing the popularity column? Is it because I'm using a single line of code? See the same thing. So the question says, based on the four means, you just calculate a pop mean, which statement is true? Marine frame means the sampling distribution mean can be used to be estimate population mean, but that is not the case with the bootstrap distribution. Okay, let's calculate standard deviation in four different ways. Hmm. Let's get this error again. Just to troubleshoot later though. Well, the tested the calculate the sample deviation by default. Okay. We know it. So I'm going to get some error there. Let's come back to that. So superb standard deviation. This is an important property of the bootstrap distribution. When you don't have all the values from the population or the ability to sample multiple times, you can use bootstrapping to get a good estimate of the population standard deviation. Okay, that's good to know. So let's look how to score the confidence interval levels. Confidence intervals.
In the last few exercises, you looked at relationships between the sampling distribution and the bootstrap distribution. One way to quantify these distributions is the idea of values within one standard deviation of the mean, which gives a good sense of where most of the values in the distribution lie. In this final lesson, we'll formalize the idea of values close to a statistic by defining the term confidence interval. Consider meteorologists predicting weather in one of the world's most unpredictable regions, the northern Great Plains of the US and Canada. Rapid City, South Dakota was ranked as the least predictable of the 120 US cities with a National Weather Service forecast office. Suppose we've taken a job as a meteorologist at a news station in Rapid City. Our job is to predict tomorrow's high temperature. We analyse the weather data using the best forecasting tools available to us, and predict a high temperature of 47 degrees Fahrenheit. In this case, 47 degrees is our point estimate. Since the weather is variable, and many South Dakotans will plan their day tomorrow based on our forecast, we'd instead like to present a range of plausible values for the high temperature. On our weather show, we report that the high temperature will be between 40 and 54 degrees tomorrow. This prediction of 40 to 54 degrees can be thought of as a confidence interval for the unknown quantity of tomorrow's high temperature. Although we can't be sure of the exact temperature, we are confident that it will be in that range. These results are often written as the point estimate followed by the confidence interval's lower and upper bounds in parentheses or square brackets. When the confidence interval is symmetric around the point estimate, we can represent it as the point estimate plus or minus the margin of error, in this case, 7 degrees. Here's the bootstrap distribution of the mean flavour from the coffee dataset. We can calculate the mean of these resampled mean flavours. If we create a confidence interval by adding and subtracting one standard deviation from the mean, we see that there are lots of values in the bootstrap distribution outside of this one standard deviation confidence interval. If we want to include 95% of the values in the confidence interval, we can use quantiles. Recall that quantiles split distributions into sections containing a particular proportion of the total data. To get the middle 95% of values, we go from the 0.025 quantile to the 0.975 quantile, since the difference between those two numbers is 0.95. To calculate the lower and upper bounds for this confidence interval, we call quantile from NumPy, passing the distribution values and the quantile values to use. The confidence interval is from around 7.48 to 7.54. There is a second method to calculate confidence intervals. To understand it, we need to be familiar with the normal distribution's inverse cumulative distribution function. The bell curve that we've seen before is the probability density function, or PDF. Using calculus, if we integrate this, we get the cumulative distribution function, or CDF. If we flip the x and y axes, we get the inverse CDF. We can use scipy.stats and call norm.ppf to get the inverse CDF. It takes a quantile between 0 and 1 and returns the values of the normal distribution for that quantile. The parameters of loc and scale are set to 0 and 1 by default, corresponding to the standard normal distribution. Notice that the values corresponding to 0.025 and 0.975 are about minus and plus 2 for the standard normal distribution. This second method for calculating a confidence interval is called the standard error method. First, we calculate the point estimate, which is the mean of the bootstrap distribution, and the standard error, which is estimated by the standard deviation of the bootstrap distribution. Then, we call norm.ppf to get the inverse CDF of the normal distribution with the same mean and standard deviation as the bootstrap distribution. Again, the confidence interval is from 7.48 to 7.54, though the numbers differ slightly from last time, since our bootstrap distribution isn't perfectly normal. Let's calculate some confidence intervals.
Okay. When reporting results, it is common to provide a confidence interval alongside an estimate. What information does that confidence interval provide? Okay. Hmm. All values. So I'm confident you are correct. Confidence intervals account for uncertainty in our estimates of a population parameter by providing a range of possible values. We are confident that the true values lies somewhere in the interval specified by that range. Okay, now let's produce some confidence interval calculation. It says you have learned about two methods for calculating confidence intervals, the quantile method and the standard error method. The standard error method involves using the inverse cumulative distribution function, inverse CDF of the normal distribution to calculate the confidence intervals. In this exercise, you perform these two methods on the Spotify data. Okay, let's see. Here 95% confidence interval using the quantile method on the bootstrap distribution, setting the 0.025 quantile as lower and 0.975 quantile as the upper quantile. Very interesting. Let's run the code and see. Voila. Let's see it in action here. I don't have bootstrap defined yet, so it won't work. It says so the five populations and bootstrap distribution are available as pandas and numpy are loaded with the usual alias and num has been loaded as sci-fi.stats. Okay, let's submit and see. We have one more to go. The 95% confidence interval level using the standard error method. Okay, I want to use the standard error method from the bootstrap distribution, and it says calculate the point estimate as the mean of bootstrap distribution and the standard error as the standard deviation of the bootstrap distribution. Calculate lower as 0.025 quantile of the inverse CDF from a normal distribution with mean point estimate and standard deviation and standard error. Calculate upper as this quantile of the same inverse CDF. That's a lot of calculation there. Let's see. Our point estimates. While the upper is E. We have a result there. I have that bootstrap. I've not imported bootstrap from Sapphire the stats. Yes. Standard excellent. The standard error method for calculating the confidence interval assumes that the bootstrap distribution is normal. This assumption should hold if the sample size and the number of replicates are sufficiently large. Oh, wow, we've completed those. What's called bootstrap distribution.
Congratulations on completing the course. We've covered a lot of ground. In Chapter 1, you learned about the basic principles of sampling, the problems caused by selection bias, and what pseudo-random numbers are. In Chapter 2, you learned how to perform the four most common methods of sampling: simple random sampling, systematic sampling, stratified sampling, and cluster sampling. In Chapter 3, you learned how sample size affects estimates of population parameters, how to use repeated sampling to generate a sampling distribution, the difference between approximate and exact sampling distributions, and you encountered the central limit theorem. Finally, in Chapter 4, you learned how to perform bootstrapping to estimate population parameters from a single sample, what the standard error of a statistic is, and 2 ways to calculate confidence intervals. There are 2 results from the last chapter that are really important for hypothesis testing, and it's important to make sure you understand them. Firstly, the standard deviation of a bootstrap distribution statistic is a good approximation for the standard error of the sampling distribution. Secondly, you calculated confidence intervals for statistics using both the quantile method and the standard error method, and they gave very similar answers. That means that the normal distribution tends to be a good approximation for bootstrap distributions. Sampling is tremendously important in many areas of data science. It is used heavily in experimental design, such as designing A/B tests. It's a cornerstone of hypothesis testing and inferential statistics. Finally, understanding sampling is crucial to understanding concepts in probability and Bayesian statistics. Congratulations again. Happy learning.
Thank you. Simply is kind of highly technical. You need to know a lot of stuff. Voila. So we are moving to the last lesson, which is the hypothesis testing in Python. Hmm. Just one more course to complete. We have to complete this tomorrow, which is the hypothesis testing. Learn how and when to use common hypothesis tests like t-test, proportion test, and chi-test in Python. Oh, then we have this last project, hypothesis testing with men's and women's soccer matches.
Hi, I'm James. Welcome to this course on hypothesis testing in Python. To start, let's look at a real-world example where a hypothesis test was crucial in a decision-making process. In 2013, Electronic Arts.
So we are going to continue this on day 75. Alright, so that'll be in the live stream for day 74. I'll see you tomorrow, day 75, as we complete this whole chapter, this whole course on hypothesis testing within 2, 3, 4 hours. Bye for now.